Hi, and welcome to Advanced Machine Learning. I'm Victor Banks. Right now we will continue our considerations about the online gradient descent algorithm, which we came up with for tackling the online convex optimization problems. And in order to analyze it regarding its regret bound, we will take a look again at the connection between the online gradient descent and follow the regularized leader algorithm, which is coming from the linearization of the convex functions which we used previously. And this will more or less immediately give us a regret bound for the online gradient descent algorithm. And then we will compare this bound for the regret with the lower bound, which is essentially telling us what's the theoretical limit for any online learner for an online convex optimization problem. So let us recall what the online gradient descent algorithm is doing. So it has a parameter which is its step size, very similar to the gradient descent algorithm we know from optimization. And it's choosing the action as follows. So the next action is given by the previous action, which we update into the direction of the steepest decrease of the current loss, which is represented by the gradient of the loss function evaluated at the most recent points. And we do this update with a certain step size, namely the step size eta we have here. And this is what we will do during the entire learning process. Again, this update formula holds only for the case where the action space is RD. Otherwise, we have to project it onto the action space. And as before, the first action is chosen arbitrary. Let's recall how we derived this online gradient descent algorithm. So more or less, we used artificial data points, which were nothing else than the gradients of the loss function evaluated at the most recent data points, namely the action we used in time step t and the environmental data point we observed in time step t. And if we now consider that this here is in fact the environmental data point which we give to the follow the regularized leader algorithm with L2 norm regularization, and assuming that we have a linear loss function, then we remember the update formula for the action of the follow the regularized leader algorithm with this L2 norm regularization is very similar to what we had before for the online gradient descent, namely previous action is update into the direction of this artificial environmental data point with regularization magnitude or step size eta. And now we do the substitution back, which we did here. So we have here this substitution of this artificial environmental data point. And well, we almost have what is here in the online gradient descent. The only difference is currently that here we have an action which is chosen by the online gradient descent, and here one by the follow the regularized leader. But if you start with the same action for both of them, for the follow the regularized leader and the online gradient descent, then, well, for the first time step, it's quite obvious, or rather the second follow the regularized leader is A1 FTRL, then this green box, plus this green box, and well, if this here holds, then this here is A1 online gradient descent plus the green box, which is then the same as for the online gradient descent, what we would do in the second time step. And from there, it's quite easy to see that all the subsequent actions will coincide, to follow the regularized leader choices and the online gradient descent choices. So you see, if we assume that the environmental data points are these artificial environmental data points we have here, we pretend that we have a linear loss. So we are tackling an online linear optimization problem with the follow the regularized leader algorithm with this regularization, then both coincide, online gradient descent and follow the regularized leader. This brings us to the following consideration for the regret bound, which we already have seen in some parts previously, but let's once again consider it in more detail. So what we are interested in when we want to analyze the online gradient descent for an online convex optimization problem is the regret we suffer for the convex loss function L, which we include here in the index in this regret notation to make it more explicit, on the real environmental data points, on the sequence of environmental data points we will see, these ZTs without the tilde. And this is by definition, what is this? Well, it's the difference between the cumulative losses which we incur by our online gradient descent algorithm compared with the cumulative loss the competing action A tilde will incur. But importantly, we have here the convex losses, and we have it for the original environmental data points. Now, our linearization of the convex loss function is telling us this here is upper bounded by the linear loss function if we make the substitution with the environmental data points, namely we substitute it with the gradients evaluated at the most recent data points, so the current action and the current environmental data point. So what we are doing here, we are changing first of all the loss function. We have now the linear loss function. Plus, we are changing the environmental data points. Now we have these artificial environmental data points. And now, when we assume that the first action used by the online gradient descent is the same as the one chosen by the follow the regularized leader algorithm, which is tackling more or less this online linear optimization problem, with these kind of environmental data points and a linear loss function, then we can make the substitution, as we saw on the previous slide, that these actions here can be substituted by the actions of the follow the regularized leader algorithm. And if you look now where we are, we have here the linear loss, or rather the cumulative linear loss incurred by the follow the regularized leader algorithm for this artificial environmental data point, and we compare it with the same competing action A tilde and what its cumulative loss will be for, well, the same artificial environmental data points. So what we get is here nothing else than the regret of the follow the regularized leader algorithm for the linear loss function, and if we would feed it instead with these artificial environmental data points. Yeah. So once again, just to make it very clear, we have that the regret of the follow the leader algorithm, regularized leader algorithm rather, with L2 norm regularization for an online linear optimization problem with the artificial environmental data points is an upper bound for the online gradient descent algorithm, rather it's regret for the original environmental data points. So what we can do in order to analyze the regret of the online gradient descent algorithm for the original environmental data points, we can simply analyze the follow the regularized leader algorithm for an online linear optimization problem where we make the substitution with the artificial environmental data points. But we remember we did already a theoretical analysis of this latter regret of the follow the regularized leader algorithm for any online linear optimization problem where we have a couple of simple assumptions, let's say, but still very general, and this can be more or less used to analyze the online gradient descent with this relationship immediately. So what we get as a corollary right away is that the online gradient descent algorithm for an online optimization, convex optimization problem, very important, where we have to assume that the loss function is differentiable to use these first order characterization of convex loss functions. And we know this here is what we saw before, bounded by this here with the z tildes, but this in fact we have seen is bounded by a bias term plus a variance term. And well, the bias term is the one we had before. There's nothing different here. It's specified by the competing action A tilde, or rather it's the Euclidean length. And the variance term, well, it was specified by the variation of the environmental data points in terms of their Euclidean squared length. And now we are using these artificial environmental data points, or we pretend them that these are the environmental data points. So we get here in the variance term accordingly the variation of these artificial environmental data points in terms of their squared Euclidean length. We can do the substitution of these artificial environmental data points. They are nothing else than the gradients of the original loss function evaluated at the most recent data points consisting of environmental data point and action. And we get immediately a bound for the regret of the online gradient descent for time horizon t for some competing action A tilde, any we like. And again, we see here a trade-off between the bias term and the variance term regarding the choice of the step size of the online gradient descent. Once again, we would like to have that the bias is as small as possible, 0, which can be achieved by making the eta, the step size, as large as possible. But then we have the problem that the variance term will grow. So we have here rather the tendency to make it small, which in turn would lead to the problem that the bias term will be larger. But we can again balance here off the trade-off. And if we make some assumptions quite similar to the ones we had for the follow the regularized data on some online linear optimization problem, where we now have to take into account that we have a new variance term with these squared lengths of the gradients. We can get the following result if we use the online gradient descent algorithm on some online convex optimization problem with a convex action space, which can be a subset where we then have to project in the worst case for choosing the actions. And the action space is such that we can find a radius b such that all actions in terms of their Euclidean length are within this radius b, inside this ball of Euclidean ball of radius b for some finite constant b. And for the gradients, which are occurring here in the new variance term, we can bound them for any combination of action and environmental data point by some constant v. Now this is quite similar to what we had before. Before we only considered the supremum over the environmental data space, where we had the z here instead. And we assumed that this is then bounded in terms of its Euclidean length by v. And then if we choose as the step size eta for the online gradient descent, more or less the same step size we had before for the follow the regularized data algorithm, we get a bound on the regret with respect to the best action in hindsight. So you don't see here an a tilde anymore. So this means that we are competing with the best action in hindsight. And this regret is bounded by this constant b times the constant v multiplied with square root 2 and multiplied with the square root of t. And again, this is a good result because this is telling us this is sublinear, it's small o of t. It's not growing linearly with the time horizon, but rather like a square root of the time horizon. So the average regret is tending to 0 per time step. And the question now is this a good result? Can we do better? And we will see, no, this is in fact already the best we can do in terms of the dependency on the time horizon, capital T, because we can show the following result. So it's a lower bound in the sense that for any online learning algorithm, so you can think of the most sophisticated one, so you can do whatever you want as long as you stick to the game rules, that you respect the game rules, that you don't use more information that you have available, so you don't cheat, in fact. And no matter how you make use of the information, you can construct an online convex optimization problem, which is characterized, of course, by a convex loss function. So in the first component, it's convex with respect to its action component. You can construct an action space. For instance, you can simply use here this rectangle or this cube with length 2b in each dimension for some constant b, and where the gradients will be bounded. All the gradients you can have are bounded in terms of their Euclidean length by some finite constant v. For every pair is this here an upper bound, even for the supremum. And your algorithm will still have a regret which is growing at least as square root t in the worst case. So this is telling us that the result we just have seen for the online gradient descent algorithm, where we have here the growing behavior of square root of the time horizon, this cannot be improved in the worst case. Yeah, so you can always construct an online convex optimization problem where more or less the assumptions are more or less the same as we had before. Yeah? Perhaps this year is a bit different, but well, we can also relax it. And still, the regret will grow as a square root of the time horizon. So, in a sense, this is showing us that online gradient descent is optimal with respect of its dependency of the time horizon. For the proof of this result, in fact, you simply use a linear loss function. Yeah? The convex loss function to prove this result is in fact the linear loss function, which is not surprising because the linear loss function is kind of a hard loss function to optimize over the time. But we see it doesn't matter which loss function we have as long as it's convex and the action space and well the gradients are bounded in the sense that their gradients are always bounded. We can always use the online gradient descent, which is, in terms of its regret analysis with respect to the time horizon, optimal.